Hi, everybody. So we've talked a little bit about how a system of linear equations can sometimes have a unique solution, but it can sometimes have no solution, and it can sometimes have an infinite number of solutions. So I wanted to talk a little bit more about how you can tell the difference between those situations. First of all, let's recall that the way we've learned to solve a linear system is by first writing it as an augmented matrix, and then performing Gauss-Jordan elimination to get it into reduced echelon form. And then, essentially from the reduced echelon form, you can read off the solution. So what are the things that can happen here? Just for example, let's say that you have a system of 3 equations and 3 variables. What are the different possibilities for what the reduced echelon form could look like? Well, one possibility is that you could have a pivot in each of the first 3 columns, and then the reduced echelon form would look something like this. So here I've circled the pivots in yellow just for emphasis, and you can see that each pivot is to the right of the one above it, and each pivot is equal to 1, and each pivot is the only non-zero entry in its column. And I've used stars on the right just to indicate entries in the matrix that can be anything. So the star you should just think of as a blank spot that can be filled in by any number. And if you were to convert this back into a system of equations, you would see that the equations would just be x1 equals something, x2 equals something, x3 equals something. So you would have a unique solution in this case. Okay, so let's look at another possibility. So it's possible for there to be 3 pivots, but where one of the columns gets skipped somehow. So here's an example of that. This is reduced echelon form. Each pivot is to the right of the pivot above it, and each pivot is a 1, and each pivot is the only non-zero entry in its column. Now, what can we say about the solutions here? Well, if you look at that last equation says that 0 is equal to 1. Well, that's impossible. So in this case, there's no solution. And that's all there is to say about that. So now let's look at another possibility. In this case, there are only 2 pivots. That last equation just says that 0 equals 0, which is always true, and so we can basically ignore that. And so we really just have these 2 equations. And in the first equation, you can solve for x1. In the second equation, you can solve for x2. And x3 would be a free variable. So here you would have an infinite number of solutions because you have this free variable x3 that can be anything, and that would give you an infinite number of solutions. And there could also be the possibility of just one pivot. And so in this case, x1 is a pivot variable, x2 and x3 are free. And so you have, again, infinitely many solutions, but there's a sense in which there's more infinitely many solutions than there was in the previous example, because here there are 2 free variables instead of just 1. So in the previous example, the solutions formed a line, and in this example, the solutions would form a plane because there's 2 degrees of freedom. So there are other things that could happen, but these examples are good enough to illustrate some general principles. So what are the things that can happen when you put a linear system in reduced echelon form? So one of the things we saw is that if that last augmented column has a pivot, then there is no solution, because the only situation where that happens is when that equation for that row with the pivot says that 0 is equal to 1. In this case, the terminology that we use is that we say that the system is inconsistent. It does not have any solution. But this issue with the last augmented column having a pivot is really the only thing that can go wrong. Otherwise, you'd be able to solve for each of the pivot variables, and you would find at least one solution. So if you don't have a pivot in that last augmented column, then there is at least one solution. The system is consistent. So then the question is, how many solutions are there? And what we know is that whenever a variable appears as a pivot, you can solve for it. So those variables are determined, and it's the variables that are not associated to pivots that are free. So if there are no free variables, then the solution is unique. And otherwise, the set of solutions is parameterized by the free variables, meaning that you can set the free variables to be anything, and you'll get a different solution depending on what you set the free variables to be. And so you have these degrees of freedom in choosing what the solutions are. And so in particular, in this case, there would be infinitely many solutions. Okay, so pop quiz. How many solutions can a linear system of equations have? Well, based on what we just discussed, there are exactly 3 possibilities. There could be no solution, 1 solution, or infinitely many solutions, and those are the only possibilities for what can happen. So that's already pretty remarkable that we can say that about linear systems. But there's something else that's pretty remarkable if you look back at the discussion we just had. You'll notice that there were hardly any numbers or calculations. All that we really had to do was look at where the pivots were in the reduced echelon form of the matrix. And based on knowing where the pivots are, we could answer this question of how many solutions. And we could even answer the question about how many free variables there are, so how many dimensions of solutions there are. So let me give you an example situation just to describe the power of this way of thinking. Suppose we had a system of equations with 4 variables, but where there's 3 equations. So then the augmented matrix for a system like this would look like this. So there's 3 rows, because there's 3 equations, and then there's 4 columns plus 1 augmented column to represent the right side of the equation. So now suppose we did Gauss-Jordan elimination and put the system in reduced echelon form. How many pivots could there be? Well, there can't be more than 1 pivot in each row. So the most number of pivots there could be is 3. So what does that tell us? Well, it's possible that one of those pivots is in the augmented column, in which case the system is inconsistent. So for example, that could occur if the reduced echelon form of the matrix looked like this. On the other hand, the system could be consistent, in which case all of the pivots are on the left side of that vertical line. But there can't be a pivot in every column, because there are 4 columns, and there can only be 3 pivots at the most. And here are a couple of examples of that. You'll notice that in every case, there's at least 1 free variable, because there are 4 variables and there can only be 3 pivot variables at the most. So there's always at least 1 free variable. And so what that means is that in the situation of 4 variables and 3 equations, it isn't possible for there to be a unique solution to the system. There's either no solutions, where the system is inconsistent, or there's an infinite number of solutions where the system is consistent, but there has to be at least 1 free variable. And what we saw here would happen anytime there are more variables than equations. So in this case, it was 4 variables and 3 equations. But in general, if you have more variables than equations, then you won't have enough pivots to fix all of the variables. So either the system is inconsistent, or it would be consistent with some free variables, and you'd have an infinite number of solutions. And so what that means is if you want to have a linear system with a unique solution, then you need to have at least as many equations as you have variables. All right, that's everything I wanted to say here. Bye.